FRC. The topic I'm going to present is fiber reinforced concrete. I had a presentation for durability of LNG tanks, but this one I shared with Corolla, so I skipped mine and I'm just presenting a couple of slides here. So the topic here is the design here in some of the general guidelines here and properties, and then the design in Europe is going to be presented by Corolla. I touch base on sustainability a little bit, and then she covers, as I said, the European design, durability, and practical applications. The focus here will be steel fiber reinforced concrete and polypropylene fiber reinforced concrete. So basically, right now, currently in ACI 544, which is a FRC code, they classify fiber reinforced concrete composite under tensile loading to strain hardening and strain softening. And then you can go one step further in bending test. You can call it deflection hardening and deflection softening. So what this means is, if you have a tension test, if you just test the matrix, it's going to break at like cracking stress basically. And this is going to be very brittle behavior. If you have a typical strain softening, it's going to go down after it gets to the peak. You can go down from here, or you can have a like a peak like this and then go down. If you are strain hardened, you can go further up. So the code right now tries to use this option. But as I was talking to Corolla, they also for strain softening, they have Eurocode actually uses mainly strain softening. And deflection hardening, it's a bending test, you still have the same property. If you have this behavior in tension, we can get basically the strain hardening behavior in bending too, because bending is mainly governed by the tension here. And in all these, I should add that scale effects are very important. So you cannot just test a small sample and say your big column is going to be fine, or vice versa. And here I just show briefly, this is one option to get this kind of behavior. You don't always get a big hardening. Even this much hardening is good enough. And one method that I've seen people is just mixing different size of fibers. So basically you have the macro fibers, they call it, which is usually like 2 inches. But you can have smaller fibers on the order like ½ inch or even less, or even those small fibers are going to bridge your micro cracks, and then your bigger cracks, the bigger fibers are going to bridge. And basically through that, I don't go over the details, you can see these in the CD. You have a different, more toughening mechanism, and then your crack, you form multiple cracking, because when this wants to grow, another cracks opens up, and that's going to add to your hardening basically. The applications currently for FRC, the main purpose of FRC, if I put it in a word, is to increase damage tolerance of a structure. The applications right now in the US, at least, it's mainly from the US perspective. Standalone, they use it in sheets, in pipes, slab on grade, shells, poles. They can use it for repair, so tunnel linings, also jackets. Tunnel lining is not a repair, I should add, but this is the standalone. Jackets can basically be in combination with pre-stressed concrete and reinforced concrete as well. So if you want to retrofit something, or for beam column joints, they use it. ACI 318 actually, version 2008, actually consider fiber reinforced concrete in its code. And the other option, cases you can use is basically for cracking control. This has been more, when I remember when FRC was started, I think the main purpose was to do cracking control, because it doesn't increase your strength that much. So this leads into the sustainability that I'm going to touch briefly. Some other application is to make it hybrid with steel, like a jacket, to do fire protection basically for your steel members. So as Berit mentioned, sustainability has three parts: environment, economy, and society. I focus on the environment. So your material should have no negative impact on the environment, basically. And due to long service life of the concrete structures, usually the influence of durability on overall sustainability is large. So if you can, save a couple of years, because that's going to affect, a lot. So in production of a material and you're constructing it, you have different phases. In production of material, you can save, energy. In design and construction, you can design with low energy consumption. You can construct with green material. Life cycle analysis is where durability analysis comes into play. You put more stuff, better quality stuff to reduce permeability of concrete, to increase their life cycle. And the demolition is basically, what are you going to do with the, recycled material and the demolished concrete. The framework they use these days, a lot of green people, you start with a infrastructure application and you see, okay, I want to build a beam member, let's say, or I want to do a bridge link, What is the problem you have? Usually you have, let's say, corrosion. So when you model it with, regular material, you come into like 25-year service life. And you also measure your sustainability index. So you measure, what material were used. You say how much steel, how much concrete were used. You measure some, energy used, the amount of waste used, the amount of carbon dioxide produced, and then you start, building a material that can reduce this and can increase your life cycle. And then you go back and then you're basically working with this specific application, and then you again, and then you say, and then you go back, you tailor your material over time, and you see what is the best option. So you have to, and this is basically using only environmental. I'm not talking about the economy here. And now that I talk about the life cycle, I just, as I said, cover some of the durability aspect of fiber reinforced concrete. As you know, for fire protection, I don't know how many years ago they found out that polypropylene fiber under extreme fire, produces voids in the concrete. So that voids can reduce your steam pressure, and you're not going to have a big spalling. And against Princeton, there are different studies. They still say the air content is the major, parameter. So you don't get a lot of benefit actually putting fiber for Friesen-Thaw. For alkali attack, if you have a glass fiber, regular glass fiber is not good. These days they have alkali-resistant glass fibers. But also, the main thing with fiber, as I said, you increase the damage tolerance of structure. So you reduce the number of, you smaller the width of the cracking, you increase the number of them. So you have more smaller cracks with smaller sizes. So your permeability is going to get smaller, so you have better alkali attack. You can have better, with the same reasoning, you have better corrosion because your corrosive agent like chloride and other stuff cannot get in. And so the same thing is also with weathering and scaling. Basically, you reduce the permeability in a lot of these cases. Only the first one, it was, forming voids. And one thing I think Carola will cover on the corrosion of steel fiber, there are different studies, what is going to happen to steel fiber because they're steel, they're steel. So are they going to corrode? So she's going to cover those topics.
Try to. There are some general properties why there's an increasing demand coming from, especially from a contractor, that he wants to design some structures with steel fiber reinforced concrete. Why is that? One reason is that the fibers give concrete ductility. We have an increased residual tensile strength after cracking, which we can actually use for the design. Fibers increase bending capacity and impact resistance. The fibers prevent local damages because the fibers are reinforcement in all directions. The fibers distribute cracks and reduce crack width. This is a very interesting issue. They have an increased durability compared to the traditional reinforced concrete. It's simple and therefore time saving. You have to put the fibers in the concrete mix. You do not need to bend the reinforcement, to couple the reinforcement and so on. It's very easy, and therefore it's also cost reducing. And at the last but not least, due to the higher durability, and this is a point for the client, you have reduced maintenance and repair cost. As Freiburg said, in Europe we're using the fibers, first of all, its structures in a strain softening material. This means the first crack must not be the last one. This is where we're using it, the steel fiber reinforcement. You should be aware of, if you use steel fiber for the first time, that the concrete mix, the casting technology, and the quality is very important and may require some additional testing. I can tell you that the type of aggregate has a tremendous influence on the tensile capacity of the steel fiber reinforced concrete. For steel fiber reinforced concrete, it's the tensile capacity and not the compressive strength capacity, which is the decisive structural parameter. We design according to the tensile capacity. And the type of aggregate has much more influence on the tensile capacity of concrete than on the compressive strength. We used in Denmark a concrete mix which has been very well used in Germany for steel fiber reinforced concrete. The only difference was that we used Danish aggregate compared to German aggregate. In Germany it was the round aggregate from the River Rhine. In Denmark we used crushed aggregate, and it was a disaster. When we made the bending test, the tensile bending test, we didn't achieve the required tensile capacity. It was 2 classes below the concrete tested in Germany. This is very important. The aggregate has a tremendous influence on that. And let me see that right from the beginning. Steel fiber reinforced concrete cannot compare with normally traditional reinforced concrete.
Can I ask a question?
Yes.
Why would we be talking about durability and steel fibers in the concrete for an exterior structure? It seems like we're going to have the chloride ion applied right directly to the surface of the concrete that has these steel fibers, and it would just accelerate the deterioration of the concrete. So are we talking about using these concretes where they're on internal applications?
No, I never come to that. Also, but I want first of all to design, but I can skip it a little bit, but to show you that you can see here the capacity for steel fiber reinforcement compared to traditional, and we have very low moments compared to traditional reinforcement. This means steel fiber can only be used there where we have a little amount of conventional reinforcement, or that's normally required. We cannot make a slab with steel fiber. There is a limitation. We used it very often in bore tunnels for the segmental lining, which is normally in compression. Then we used it as concrete pavements and floors for some foundations, and as shear reinforcement instead of traditional stirrups in pre-stressed members. There is also a use for it in prefabrication and in repair. And the last one is the combination of steel fiber reinforced concrete and traditional to reduce the crack width. And this is interesting always in the case where the correct width